Hello, everybody. Welcome back. So, today we're going to be talking about permutations with some identical items. So, last time we talked about permutations in general, but ones that didn't have repeated items, like a school locker combination where we have, three different numbers and they all have to be different. We can't just choose the same number, or, a house number where apparently we couldn't have repeated digits, even though for a real house number we could, but for the sake of the question, we couldn't. But what happens when we are able to repeat digits, right? Think of things like a phone number, for example. Are we allowed to repeat digits in a phone number? Well, yes, absolutely we are. So um, there's going to be times like that where we need to make sure that we're accounting for the fact that we have some identical items in there. So this one, it's definitely items. Before I was saying, oh, it could be items or people for the last one. In this one, it's definitely got to be items because there's no two people exactly alike, right? Even two twins are not the same person. They are two separate people, even though they look the same and they're the same age. They're two different people. Whereas when it comes to things like numbers, well, the number six, if we have the number six twice in a row, well, that's just the same number. They're not unique, not at all whatsoever. Or if we have the word be, these two e's are the same. I could swap the two e's around, and it would still say be. It would still be the exact same permutation, right? And so, in these kinds of situations, there are going to be identical items, right? All right. So here we have a formula. It says if n items are arranged in order, but there are a identical items of one type, b identical items of another type, and c identical items of another type, then there is n factorial over a factorial, b factorial, c factorial, etc. ways of doing so. Now, before I get into this question, I want to talk about why that is. Or actually, you know what? I'm going to use this next example as a way to explain why this is. So, first, we're going to take this for granted, and then I want to kind of illustrate why this formula holds true for this simple example, and hopefully expand upon why it's true for all examples as well. There won't be a full-blown proof here, but I do want to kind of explain and make sure it's clear as to why this formula is the way it is, because it's a lot easier to remember this formula if it's understandable to you rather than if it's just a bunch of gibberish that you're only following because, well, that's what's on the paper and that's what you have to do. So let's do that. It says here, how many permutations are there for the letters in the word be? Well, the thing is, there's n would be 3 here, right? There's 3 letters. And then there's 2 e's, right? So a would be equal to 2, right? There's 2 different e's. However, there's only one different b, and so there's not b identical items of another type or c identical items of another type or anything like that. There's only 2 identical e's, and that's the only identical thing that I see in this word, which makes sense because there's only 3 letters in this word. So how many identical items could we really have? Not that many, hopefully. So let's put that in. So here I have 3 factorial over 2 factorial, which is just going to give us 3. So therefore, there's 3 permutations for letters in the word be. I keep almost saying combinations, but combinations are something different. I need to call these permutations and not get mixed up with combinations. Yes, so these are permutations. There are 3 permutations or 3 ways we can arrange the letters in the word be. Now let's talk about that. Here's the thing. If we just kind of write out what are those 3 arrangements, of course, one of them they already gave to us in the question, it's B. The other one is EBE. The other one is EEB, like that, right? So those are the 3 ways we could do it. Now, normally, if we have a 3-letter word, there's 6 ways to arrange it, right? There's 6 ways to arrange those letters, or there's 6 permutations. And here there would be 2, except that the E's are the same. So if we were to swap around these E's, we would get the same thing. We'd get BEE again, right? However, if the E's were actually different letters, then this would actually, then switching around letter 2 and 3 would give us a different permutation. Same with here, right? We could argue the same thing. We could rearrange these 2 letters, these 2 E's, we get the same thing, but we normally wouldn't, right? Or same with here. We rearrange these 2 letters and we get the same thing. Voila, right? And so that's why, right? That's why, however many identical items there are, if we swap them amongst each other or between each other, then the overall permutation does not change, right? And so that's why, let's say there were three e's. Well, if we, swap them in any of the six ways, any of the three factorial ways we could, it doesn't change the overall permutation whatsoever, right? So, or what if there were four identical ones? It would be over 4 factorial. Not that we could have four identical things in a three-letter word, but you get what I'm saying here, right? If we have 4 factorial identical things and we swap them around in any of those 4 factorial ways, any of those 24 ways, we swap them around, we switch them, we have the exact same thing. And so that's why we're dividing by that number, because that number of factorials, that number of permutations of ways that those identical objects could flip, because flipping them, switching them in any of those ways doesn't actually change a thing about the overall outcome. Okay, so I hope that made good sense as to why this is. I think this is a really cool one, actually, a very cool technique to use. So I hope you think so as well. So, with that said, how many permutations are there for letters in the word minimum? So, first of all, how many letters are in the word minimum? 1, 2, 3, 4, 5, 6, 7. So, 7 letters. And there's clearly quite a few repeats. There's M, 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 so there's 3 M's. There's 2 I's, I, and then there's only 1 N, and there's only 1 U. Okay, so in that case, the answer would be 7 factorial over 3 factorial, 2 factorial, right? And we could leave it like this in some cases, or we could figure out what that is. And I'm actually going to solve and figure out what that is. I don't feel that these numbers here are so big that, figuring it out would just make it arbitrarily large. I do think it's worth actually figuring it out here. So I'm going to write that down. 7 times 6 times 5 times 4 times 3 factorial over 2 times 3 factorial, because in this case 2 factorial is just 2, so I'm just writing 2 there. Keep in mind, though, that if it was not 2, right, if it was something else with factorial, it wouldn't just be the same. But in this case, it is. And then I can cancel those out and make this a 2. And then let's multiply those last few things out there. So 7 times 6 times 5 times 2 is going to give us 420. So there are 420 ways to arrange the letters in the word minimum, right? Whereas if we didn't have repeats, there would be more ways, because we could arrange any of the 3 M's any way we want, and we're still going to get the same permutation overall. And same with the I's, the 2 I's as well. We could switch them and nobody would know it would be the same thing. Very good. All right, example 3 says, in how many ways can a basketball team of 12 take a team photo? Picture lining up from left to right, where from shortest to tallest. If there is 3 players, I think they meant if there are 3 players who are 6 feet tall and 4 players who are 6'6" tall. Okay, so let's think about that. In this case, even though these people are not the same, they are the same height. And so in this case, actually, we can use people as an example because we're rearranging in terms of height, right? So the 4 players who are 6'6", they can switch, and even though that's a different, permutation technically, in this case, we just want to know how many ways we can arrange them from left to right, from shortest to tallest, right? And any way that those 4 people switch would still have the overall permutation be shortest to tallest. Or same with the 3 people who are 6 feet, they can arrange themselves however they'd like amongst themselves, and they are still going to be there, right? So to do this, we would say 12 factorial over 4 factorial, 3 factorial, right? Because the 12 factorial is how many ways we can arrange 12 basketball players overall, right? And then 4 factorial, 3 factorial. Now, the trouble is, what does this do? Does this necessarily guarantee that we have the players shortest to tallest? Well, no, it absolutely doesn't, right? Because 12 factorial being on the top actually implies that we're considering all different ways, and then we're just making sure that the 4 people can swap and it doesn't change anything, and the 3 people can swap and it doesn't change anything, right? But actually, there's only one way to line everyone up shortest to tallest if everyone is different heights. The reason that there are multiple ways to do it is because some players are 6 feet, and so they can arrange, right? And we still have this outcome we want. And same with the 6'6" people, right? We can arrange them and we still have the outcome that we want. And so in this case, we're actually going to get rid of this 12 factorial entirely and say, well, the answer is just 4 factorial, 3 factorial, because everybody else is structured, right? Shortest person must go first, then second shortest, then third shortest, etc., until we get to those 6 feet people, and they can arrange amongst themselves in any of 3 factorial ways. And then we eventually get to the 6'6" tall people, which are very, very tall, and they can also arrange themselves in 4 factorial ways. And so therefore, we actually just need to say 4 factorial, 3 factorial, and that's the answer, right? So that's the answer. So therefore, we have 24 times 6, which is a good question, 144. So therefore, there are 144 ways that the team of 12 can take a team picture, lining up from left to right, from shortest to tallest, if there are 3 players who are 6 feet tall and 4 players who are 6'6" tall. Very good. All right, example 4 says there are 15 marbles in a bag. 9 of the marbles are black, 4 are red, and 2 are blue. In how many ways could you select those marbles from the bag if they are removed one at a time? So basically, how many ways could we order these 15 marbles in? Well, let's think about that. So overall, if we had just 15 marbles in a bag and we're pulling them out and putting them in order, right, in a certain order, if they were all different colors, there would be how many ways? There would be 15 factorial ways. However, we have some repeats here. We have 9 are black, so this would be over 9 factorial. 4 are red, so 4 factorial. And 2 are blue, so 2 factorial, like that. And then there we have it, and that's the answer. This one, it's going to be an extremely high number, and so I'm actually not going to continue to solve. I'm just going to call this good and say this would be our answer for this one. Very good. All right, so this one, it's a good lesson, and I think it's also important. One big piece of advice here with permutations is that as long as you understand what the question's asking and figure out what type of question it is, the actual formulas are not that hard, right? It's not that hard to just follow this formula or follow one of the previous formulas. What is hard is, or at least is harder, is to understand, well, which formula should I use, right? Which formula makes sense given the situation, right? For here, if we just read 12 and then, there's 3 repeats, 4 repeats without really reading the question, we could have said, oh, it's 12 factorial over 4 factorial, 3 factorial, and not realize that no, the only people who could actually move in these situations and still have it be shortest tallest are these specific people. So we only want to figure that out. We don't actually want to find out, how many how many ways in all they could do it if these people switching doesn't change the permutation supposedly, right? And so that's very important. That's important to keep in mind, is to make sure you understand what is the question asking, so you can choose the correct equation, so you can do what does make sense rather than just randomly choosing an equation and hoping that it's the correct one, because unfortunately that will not always work. That might sometimes work out in your favor, but it will not always work out in your favor. But yeah, that's pretty much that. That's permutations with some identical items. Next time we'll talk about Pascal's triangle, which is actually it's going to be interesting. It's a bit different from permutations, but it's also an interesting topic that I hope everyone enjoys. But until then, we'll see you for the next class. Bye, everyone.